Okay, guys, I'm going to go through motion of charged particles in magnetic fields. So on this diagram to the left, I have a charged particle, a positive charged particle, and its velocity is moving to the right, which is perpendicular to a magnetic field directed into the page. Now, in the last bit of work, we learned about how to find the force, both the magnitude and the direction of the force on a current element. All right, so let's go back to that for a moment. All right, the force, the magnitude of the force was given as F equals I delta L. Sorry, forgot one thing. Forgot the magnetic field strength. All right, F equals B I delta L. All right, now we're going to have to do this in terms of some other characteristics of this charge. But consider this. For delta T, so for a short amount of time, delta L equals V delta T, and current, by definition, is charge per unit time. Okay, so what you actually end up with is this equation. I'm going to write it over to the right. Actually, I'll start it here. You'll see what I mean. Let's substitute what we just discussed in there. So keep the B, magnetic field strength B, and I is charge over time times by delta L is V delta T. Okay, so I'm going to write the formula for the magnitude of the force on this charge entering the field. It's also this will remain the force on the charge as it's moving through the field. F equals B Q V. As you notice down here, that delta T will cancel with that delta T. All right. Clear up a bit of space. All right. So that is the magnitude of the force. F equals B QV, where V is the magnitude of the magnetic field strength, V is the velocity of the charge, and there is a Q, which is the magnitude of the charge. All right. Now, the motion of the charge from your right-hand palm rule, the direction of force, so if let's just draw a little charge entering here. Let's get my, all right. So if my charge is here, all right. Initially, its velocity is moving to the right. All right, now using the right-hand palm rule, basically for the right-hand palm rule, your velocity is the thumb. Now that's unless it's negative. We'll discuss that in a minute. But to summarize, if it's a negative charge, you point your thumb against the velocity, or some people choose to use the left hand. There's a anti-symmetry between your left and right hands that actually works very nicely. You can actually point your left thumb in the direction of a negative charge, like an electron. I'll go through examples of some of those in a minute. But the palm rule says, okay, instead of current, you have velocity. Point your thumb in the direction of velocity. All right, your fingers go in the direction of the magnetic field, which is into the page. And in this instance, the force will be going up the page. So that's your force. All right. So what you notice that the key point in this is that force and velocity mutually perpendicular. And where we've seen that before, uniform circular motion. All right. So the magnetic field, if the charge enters a uniform magnetic field at right angles to the field, it will experience uniform circular motion. I have a little diagram of that. Now, if it enters at an angle not directly perpendicular, the perpendicular component will go in circular motion, and the non-perpendicular, the parallel component, will have no force, and it will actually look like a helix, but that's not really in this course, so we're going to forget about that. It's not going to be critically important. All right, so let's just drag my little image up here. Okay. So you notice here you've got, in this image, you've got the particle moving in a circular path because the velocity and the force are always perpendicular to each other because of the right-hand palm rule. All right, so uniform circular motion. Let's remind ourselves the force. Oops. Let's use another brush. All right. So force centrifugal equals mv squared on r. Okay, now we just came up with an equation for the force, which is providing centrifugal force, which is B QV. Well, would you look at that? I can cancel one of those. All right, and then I can rearrange this formula. All right, so in that case, I can move that R across. I'm going to write this MV equals BQR, and then I've got R equals MV on BQ. Okay, now that's the key formula for motion of charged particles in magnetic fields. So let's just strip that away. Actually, no, I'm going to keep the diagram. You'll see why in a minute. I'm going to do a few other derivations. So that's derivation number 1. Make sure you know how to do these derivations. They are very important for your test. Okay, so that's equation number 1. Let's put that up there. Okay, so R equals MV on BQ. Now, a couple other neat things about circular motion with magnetic fields is there is actually a fixed period which is independent of speed in R. It is dependent on the properties of the charged particle going through circular motion and also the strength of the magnetic field. So let's go through that. Period, moving through a circle. Let's get my brush back up. So period moving through a circle, T equals circumference over time equals distance on speed. Okay, so we've got that. All right. Yes, that's correct. All right, now what I'm going to do is I'm going to take out the R and substitute in what we just discovered. Okay, now this will actually cancel the two V's. Now I'm going to write that up here. T, so there's a second equation. There's actually quite a few that you'll derive in this part. I'll only go through some of them here now. All right, 2 pi m on BQ. Okay. Just tidy that up a bit. There we go. 2 pi m on b cubed. So yeah, the period, notice that it's based on the property of the mass, magnetic field, charge, but the faster it goes, the larger the radius, but that doesn't actually affect the time it takes to complete a cycle. That becomes important when it comes to the cyclotron. Now, just a little bit on a question you may be asked is in relation to the motion of certain particles. So I've got some radioactive particles that are moving through a magnetic field. Now we're going to assume, oops, let's move you back over here. I keep forgetting to change my brush. Okay, let's assume okay, so all of these particles are entered with the same speed. That's the point I'm getting at. Okay, then what could make the paths different? Well, the key formula is this one. There's nothing in here that really tells you what time it takes for them to go around. All right. Now we have okay, we've got key nuclear particles. We've got neutrons, gamma rays. You notice that neutrons and gamma rays, they just move in a straight line because they carry no charge. They carry no charge, so they don't trace out a current element. They have no force. All right, so we can discard it. All right, we have beta particles, beta plus at the top and beta minus at the bottom. So that's a negative charge. So you notice that it goes in the opposite direction as a positive charge. It has force down where they start with force up by the right-hand palm rule. Now, the other key difference is, okay, the path that these two trace out, the beta plus and the alpha. Now, the alpha particle, let's talk about the alpha particle in relation to the beta particle. Alpha particle has double the charge, where you think, okay, if that alone was the only feature in this formula at the top, it would actually have a smaller radius, but actually has, as it says, its mass is of the order of 10 to the minus 27, actually quite a high, it's nearly 26 kilograms. I don't have the number on top of my hand, but I don't need that to make my point. Because basically the major feature, the beta particles are, the plus particle is the positron, the minus particle is the electron. They both have approximately the same mass, effectively for the course, 9.11 times 10 to the minus 31. So they're basically minus 30. So you notice that the alpha particle is about, or several orders of magnitude higher in mass than the beta particle, therefore experiences well, its radius of its path, if mass is many orders of magnitudes larger, even though it has double the charge, I put the beta plus. Beta has 1 electron charge, alpha has 2 positive charge, 1 positive charge. Okay, so you've doubled the charge to go from beta to alpha, but you've got many orders of magnitude more mass. So that's the major feature here that's changed. You notice that radius is directly proportional to mass and inversely proportional to charge, but the mass is the thing that's changed far more than the charge. So that's why the alpha particle has a much larger radius. All right. So I think that's all I wanted to do for now. I will update with another video shortly.